Section 3.2, we're going to look at series solutions at ordinary points. What's an ordinary point? Well, consider a of x, y double prime, plus b of x, y prime, plus c of x, y equals 0. So assume we have some sort of second order differential equation. The first thing we typically do with this equation is we divide everything by a of x. So we're going to divide by a of x. And we write this as y double prime plus p of x y prime plus q of x y equals 0. So p of x is just b divided by a, and q of x is just c divided by a. If p of x and q of x are both analytic at x equals c, then x equals c is called a regular point or an ordinary point, sometimes called regular, and the equation has two series solutions centered at x equals c. You should have a question on that. Your question should be, what does the word analytic mean? What does the word analytic mean? Very good question. Anybody know what the word analytic means? Analytic means that the function p of x has a convergent power series. So when I say p of x is analytic, I mean p of x has a convergent power series. And to say q of x is analytic also means q of x has a convergent power series. Okay, so I might give you something like x squared y double prime plus e to the x y prime plus 12x squared y equals 0. Is x equals 0 an ordinary, spelled ordinary wrong, ordinary point? Yes or no? You get a 50-50 chance of being right.
Yes.
Yes. No. Some of you are right, some of you are wrong. All right, well, I'm going to divide by x squared, because we typically write it in that form. So that's going to give me y double prime plus e to the x over x squared y prime plus 12y equals 0. My q of x is the function 12. Does 12 have a convergent power series at x equals 0? The power series for 12 is 12. That's correct. The power series for any polynomial is just that polynomial. If this were 12x squared plus 5, then the power series would be 12x squared plus 5. So yes, q of x is analytic. Does e to the x over x squared have a convergent power series at x equals 0?
Yeah.
No, why not? It's undefined at 0. Can you plug 0 into that?
We get 0 on the bottom.
Well, I get 0 on the bottom. Do I get 0 on top?
You get 1.
I get 1. So does it have a convergent power series?
No.
No. Something in the form 1 over 0, it's undefined. That means you have a vertical asymptote there. So P of x here is not analytic. There is not a convergent power series there because the function is undefined there. At x equals 0. So is x equals 0 an ordinary point? No. It would be called a singular point. P of x does not have a convergent power series. All right, one more of those. How about x, y double prime, plus sine of x, y prime, plus, I don't know, 6x cubed minus 9x squared, y equals 0. Is x equals 0 an ordinary point? Well, I would write it this way. Y double prime plus sine x over x, y prime, plus, when I divide this one by x, I get 6x squared minus 9x, y equals 0. Is 6x squared minus 9x analytic?
Yeah.
Yes, because it's a polynomial. So its power series at 0 is?
Yeah.
No.
It's that function.
It's that function. The power series for a polynomial is the polynomial. How about sine x over x? Is that analytic? Does that have a power series at x equals 0?
Yeah. Yeah.
Yes. How come?
1, 0, 0, 0. Some weird calculus thing.
Because it's some weird calculus thing. All right, so the difference is, for this one, I got 1 over 0. 1 over 0 is undefined. For this one, I get 0 over 0. 0 over 0 is still undefined. However, for this one, what's the limit as x gets close to 0? It would be 1. So this one, the limit as x gets close to 0 does converge. So this one does have a power series. In fact, what's the power series for sine x?
-1. It goes back and forth.
It goes back and forth. It starts with x.
Minus.
Minus
X cubed.
x cubed over
2, 3.
3 factorial. So I had a 3 and a 2. You were right both times. Plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. And it goes on forever. So the power series for sine x over x is what?
1.
1.
Cosine.
It's not cosine.
Okay, then.
Minus x squared over 3 factorial.
Minus x squared over 3 factorial. Cosine would have x squared over 2 factorial. Minus x to the 4, or plus x to the 4th over 5 factorial. Minus x to the 6th over 7 factorial. So sine x over x does have a power series solution. Does that converge at x equals 0? Can I plug x equals 0 into that power series? Yes, and I get 1. So, for case number 1, because we got 0 on bottom, it was not analytic, but it's because we got the number 1 on top. For case number 2, we got 0 on bottom, but we also got 0 on top, and that turned out to be analytic. So the answer to number 2 is, yes, x equals 0 is an ordinary point, so we are guaranteed that there is a power series solution there.
Or did you give us a handout with the forms of the common power series? Or did you just display that in one day?
I believe I just displayed it.
Okay. I thought I had some.
No, I don't think I passed out a handout. Where did it go? Somewhere here in section 3.1. Here it was. Here were your famous power series.
What page is that?
Page 195.
Should we know those or not?
I would say you should know the first 3.
I don't know.
Oh.
And you'll notice the first 3 are very related. E to the x has all the powers and all the factorials. Cosine alternates, but cosine only has the even powers with the even factorials. Sine also alternates. It has the odd powers with the odd factorials. You should probably know those three. All right, so how's this going to work in practice? Solve. X squared plus 2 y double prime plus 4xy prime plus 2y equals 0. We are always going to find power series centered at 0. In other words, our answer is going to look like y equals the sum from n equals 0 to infinity of a sub n x to the n. It's just easier than having, like, if we wanted to center it at c equals 3, we'd have to have a little x minus 3 to the n there. Just makes it a little easier to have x to the n. Is x equals 0 an ordinary point for that equation? Well, if I divide by x squared plus 2, am I going to have to worry about division by 0? No. Because if I divide by x squared plus 2, is x squared plus 2 ever equal to 0? No. So, just when I divide by 0, I'm going to have rational functions, but I won't have 0 on bottom. They're guaranteed to be analytic. So x equals 0 is a regular point. Ordinary point. Okay, so we're going to assume y looks like that. And then we're going to have to take the derivative. So that's going to be the sum. What's the derivative? N starts at 1 and goes from 1 to infinity. We're going to have n a sub n x to the n minus 1. We bring the power down and we subtract 1 from the power. How about y double prime? That's going to be the sum n equals 2 to infinity. We're going to have the n. We're going to bring the power down. That gives us an n minus 1. A sub n x to the n minus 2. Subtract 1 from your power again. All right, so there's our function. There's our derivative. There's our second derivative. We're going to plug it all in. Yeah, nice, huh? All right, we're going to have x squared plus 2 times the sum from n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2 plus 4x, the sum from n equals 1 to infinity of n a sub n x to the n minus 1 plus 2 times the sum from n equals 0 to infinity a sub n x to the n equals 0. What should I do next? Make sure all the indices are the same. Yes, before I do that, I think I need to do something else slightly first.
You need to show the powers of the x.
I need all the powers of the x to be the same. Distribute. I think what I want to do is I think I want to take the summation and distribute it over the x squared plus 2. And I also think I'm going to take this 4x here and move it in. Okay, so what happens when I take x squared and I multiply it by this summation? I get x to the n. I add my powers, don't I? All right, so this gives me the sum n equals 2 to infinity of n times n minus 1 a sub n x to the n plus the sum from n equals 2 to infinity. Move that 2 in. That's just going to give me 2n n minus 1 a sub n x to the n minus 2.
George, did you do a double step right there? Wouldn't that be n equals 1 exclamation?
No, what I did is I took the x squared and multiplied it by this. That gave me the first.
Okay, yeah.
And then I took the 2 and multiplied it by that.
Okay.
So I just took the x squared plus 2 and distributed it. Now I'm ready to do this one, and I agree this one starts at 1. But what happens when I take that 4x and move it inside?
What happens before I actually want that?
It's going to just be an x to the n now, isn't it? I add my exponents again. Max, did you have a question?
What happened to 2?
This 2?
Yeah.
It's right there.
Oh, you moved it over.
I moved it inside the summation, yep. All right, so plus. So this one I'm going to take the 4 and I'm going to slide it in, and I'm going to take the x and slide it in. That becomes the sum from n equals 1 to infinity of 4n a sub n x to the n. And even this one, I'll take that 2 and I'll slide it in. So plus the sum from n equals 0 to infinity of 2 a sub n x to the n equals 0. Okay, so now I need to correct 2 things. First off, I need all of these x's to have the same power. Do all of those x's have the same power? No, one is not like the other. Which one is not like the other? This one right here. So how am I going to fix this one? I'm going to have to add 2 right there, aren't I? That makes that an n. So I'm going to have to add 2 to that n right there. I'm going to have to add 2 to that n. I'm going to have to add 2 to that n. And then I balance it all off by doing what? Subtracting 2 from that n. Which is going to be good, because in a minute I'm going to say I also want all the n's to start at the same spot. So if I have to add 2 there and subtract 2 there, it's going to fix 2 problems at once. All right, so let me just write that one down. So this one is going to be plus the sum from n equals 0 to infinity of 2 times n plus 2 times n plus 1 a sub n plus 2 x to the n. So that fixed that one. It now starts, it has x to the n like all the other ones, and it starts at 0. This one on the end, this one is fine. It has x to the n and it starts at 0. This one's got a problem. This one has the right exponent, but it doesn't start at the right place. I want it to start at 0. So how do I fix that? Nope, don't subtract 2. Just start it at 0. Because what happens when I plug 0 in? I get 0 right there. 0 times anything is going to be 0. Or if I plug 1 in, when I plug 1 in, I get 0 right there with the n minus 1. Still 0. So that one I can just change the start. I just change it from 2 to 0. N times n minus 1, a sub n x to the n. Fixed the second one already. Third one, I think I can do the exact same trick. Can't I just start this one at 0? Yeah, because if I start it at 0, when I plug 0 in, I'm going to get 0 right there. For that n, 0 times anything is 0. So you see the 2 techniques that happen there? There's usually one of them, maybe 2, where you're going to have to shift the indices. The rest of them, you just change where they start, and it still works out fine. So we're going to have the sum n equals 0 to infinity 4n a sub n x to the n plus the sum from n equals 0 to infinity of 2 a sub n x to the n equals 0. That last one I didn't need to fix anything, it was all set. Okay, so now I'm getting happy, because now all of the x to the n's have exactly the same power, and they all start at n equals 0. So what has to happen? How do I add a whole bunch of infinite things together and end up getting an answer of 0? All the insides have to be 0. So that means I have to have n times n minus 1 a sub n, x to the n, plus 2 times n plus 2 times n plus 1 a sub n plus 2, plus 4, x to the n on that one, plus 4n a sub n x to the n, plus 2 a sub n x to the n. All that has to add up to be 0. You'll be okay. Once you do one or two of these, it'll go faster. I'm going very slowly. All right, now notice that x cannot be the number 0. If x is the number 0, then this whole summation is just 0, and we don't want the trivial solution. Since x is not 0, x to the n is not 0, and I really didn't need to write that down. I can just divide through by the x to the n. It's not the number 0. All right, so we're getting close. What we need now is we need to get our recursion relationship. So you might notice that this one has an a sub n plus 2, where all the other ones just have a sub n. So what I want to do is I want to take this a sub n plus 2 and I want to get it alone. So I'm going to write where it is, and I'm going to move everything else over to the other side. In other words, I'm going to write 2 times n plus 2 times n plus 1 a sub n plus 2 equals. Now, let's be a little bit clever here. Not only am I going to move stuff over, I'm also going to distribute in common and combined terms. So here I have n times n. N times n is n squared. So that's going to give me an n squared a sub n. And then I multiply the n through, I'm going to have a negative n a sub n. But I also have a 4n a sub n. So negative a sub n plus 4n gives me a 3n, but then I got to move it to the other side, so it becomes a negative 3. And this first one should have been negative, shouldn't it? Because I take n times n, that's n squared, but then I have to move it to the other side, so that one's a negative n squared a sub n.
So you just not looked at the minus n, not also go that yet?
The minus n, I combined with the 4n, and that gave me a 3n, but then I moved it to the other side, so when I moved it to the other side, it became a negative 3n. And then the last thing left is this one right here, the 2, so that's a minus 2 a sub n. Lots of algebra. All right, that's 2 times n plus 2 times n plus 1 a sub n plus 2 equals, factor the right-hand side. How can you factor the right-hand side? I'm going to pull out a negative a sub n. When I pull out a negative a sub n, what's left over? N squared plus 3n plus 2. But then n squared plus 3n plus 2 factors. N plus 1 and n plus 2. Well, that's very convenient, isn't it? A sub n plus 2 is negative a sub n over 2. The n plus 2 and the n plus 1s happen to divide right out. So there's all of our algebra to get our recursion relationship. Well, now, here's the deal. Here's the next problem. We started with a y double prime. If I start with a y double prime, how many answers do I need to come up with? 2. How many answers did I write down? 1. Where's the other one? Here's what's going to happen. Notice when we did these on Friday, when we had a first order differential equation to start with, we ended up with an a sub n plus 1 here, and we had the a sub n on the other side. Now we have an a sub n plus 2. So here's how we're going to create two patterns. We're going to create two patterns by over here using only odd numbers, and then over here using only even numbers, because they always differ by 2. All right, so I'm going to write my recursion relationship this way. A sub k plus 2 equals minus a sub k over 2. And I'm going to build a little table. K equals 0, k equals 2, k equals 4, k equals 6. I'm only going to plug in the even numbers. And that'll give me one pattern. What happens when I plug in k equals 0? A sub 2 is minus 1/2 a sub 0. I plugged in k equals 0, so I got 0 plus 2 there, that was 2. And then instead of just dividing by 2, I wrote it as a minus 1/2. When I plug in 2, I get a sub 4. What's a sub 4 going to be? Negative 1/2 a sub 2. But then I'm going to take a sub 2's value and plug it in. So I'm going to have negative 1/2 times negative 1/2. That's 1/4 a sub 0. Plug in 4. When I plug in 4, I get a sub 6 is negative 1/2 a sub 4. But then when I take a sub 4 and plug in 1/4 a sub 0, I get negative 1/8 a sub 0. So I think we're seeing a pattern here. Go ahead.
So you plug in a sub 4 in previous? I don't understand that.
What I did is I got this negative 1/2 a sub 4 here, but I took this answer for a sub 4 and I plugged it in right there. So I had negative 1/2 times 1/4 a 0. That gave me the negative 1/8 a 0. When I plug in 6, I get a sub 8 without doing any work. Can somebody tell me what number should be there? 1/16 a sub 0. Why 1/16? Negative 1/2, 1/4, negative 1/8, positive 16. I'm multiplying by negative 1/2 each time. All right, so this gives me one answer. So one answer is y sub 1 is negative 1/2 a sub 0 plus 1/4 a sub 0. Oh, I forgot something right here. No, what did I forget? That's almost the right answer. The right answer should start with what? It should start with a sub 0 minus 1/2 a sub 0 x squared. How do I know that should be an x squared? Because what always goes with a sub 2? A sub 2 always goes with x squared. Plus, what's the next one? 1/4 a sub 0 x to the 4th. The next one, minus 1/8 a sub 0 x to the 6th plus dot dot dot.
So close to the sign.
It's what?
Is it close to the sign summation?
Is it close to the sign summation? It looks a lot like the sign summation, doesn't it?
Yeah.
How come?
Alternating signs and even exponents.
It's got alternating signs and even exponents. So, my guess is that is somehow related to the sign formula. If you look up the back answer in the back of the book, they will give you the answer in terms of the sign function, would be my guess. When you go to take your test, this is what I'm going to want to see. I'm going to want to see that you find the first 3 or 4 terms and write it out. I don't care if you can write it as the sum of sine of 1/2 x, or whatever it happens to be, whatever series it happens to be.
So we can just leave it like.
You leave it just like that.
You showed the pattern, so.
You've shown the pattern.
Yeah, that's a good pattern. Okay.
Well, the bad news is we're only half done.
Oh, I know, do X still.
How many answers do we need?
2.
2. How many do we have?
One.
1.
Now we do take this
So
out, 3
what
minus
power
2.
is the question going to be up to 10? Second power or third
I think second power is plenty.
Yeah.
In fact, I don't think we do any problems with third power, so I think second power is plenty high.
I agree.
So you're going to come over here with your recursion relationship, and now you're going to do the same thing except you're going to use odd numbers. So you're going to plug in k equals 1, and you get a sub 3 is minus 1/2 a sub 1. Plug in the next odd number. The next number is k equals 3. A sub 5 is negative 1/2 a sub 3. But you take this and you plug it in there. 1/4 a sub 1. And it's the exact same pattern, isn't it? So I think your other solution is y2 is going to be, this one's going to start with a sub 1 x to the 1 minus 1/2 a sub 1 x cubed plus, what's the next one? 1/4 a sub 1 x to the 5th minus 1/8 x sub 1 x to the 7 plus dot 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 on and on forever. Now, a minute ago, somebody said one is sine and one is cosine. Y sub 1 that we found, y sub 1 is actually the cosine. The cosine is the one with the even powers. This one is actually a sine form. Sine is the one with the odd powers. Questions on that?
How do you do it?
How do you do it? Well, you start back up here and it goes down, and then you take derivatives, and